Hello folks. Okay, well, last time I either promised or threatened to go through and look at those different compilation steps in a little bit more detail, so here we're going to follow up on that. So we want to go through that kind of basic sequence of steps and just take a few minutes to look at each different one. So let me just get rid of my talking head here. So again, we said that we would go through, read the character sequence that makes up the actual source code file, break it up into tokens, so identifiers, keywords, the various operators, right? Break that character sequence up into meaningful bits and pieces, analyze the syntax for them to see what they mean sort of structurally, a while loop inside a for loop inside a function declaration. Augment that with the semantic meaning, do our type checking, make sure that make sure that we've checked that variables are declared before they're used, make sure we're checking scope, all that kind of thing. Produce intermediate representations of the code, right? Something that's independent of the original source code but captures all of the meaning of the program. Perform our optimizations. So the first ones we'll perform are the ones that aren't dependent on the actual target language or target platform. Generate code that is in the target language, and then do any additional optimizations that we want on that, right? So that was the basic sequence that we wanted to run through. So that first part, scanning, reading that initial character sequence, right? We're going to go through, and you've got, whatever sequence of characters makes up your source code program, your C++ program or Java or Bash or whatever it is. And then we might go through and do a bunch of sort of standardizations. So you might say, well, let's put all of the white space into a standard form. So every place where there's 10 or 12 or 30 different white space characters in a row, let's just replace them with one single white space. So put it in a standard format. There might be different forms of macros to apply, right? The pre-processing side of things, where we're dealing with hash defines and hash includes, and or dealing with templates, or dealing with macros, whatever kind of macro the language might support, where we're doing transformations to rearrange things, right? We're going through and performing any basic error checking, right? There might be cases where we realize that this particular sequence of characters can't form a valid token or can't form a valid chain of tokens, or it's got characters in it that aren't supported by the language. Right? So there's some error checking that's going to take place here. And again, go through this character sequence and divide them into recognized tokens. So if you see something like x equals 37, then maybe you distinguish, okay, x is a token. It's going to represent an identifier of some form, maybe a variable. Equals represents a token for an assignment operation. 324 represents a token for some integer. And so it's going to go through and carve up that sequence of characters into individual tokens, and it might associate some attributes with some of them. So it might say that, okay, x is a token of type variable or type identifier, and its associated value is the string x. Or it might look at 324 and say, okay, well, I recognize that as an integer token, and its associated value is 324. So there might be things like this where we go through and recognize what type of token it is, and then associate some values with it. So you've got this scanning sequence where we're taking the characters and turning them into tokens, identifying attributes. And I think I just said the exact same thing. All right, then we'll go through and we'll perform a lexical analysis on it. So we want to go through and take that sequence of tokens, I'm expanding our read sequence into our lexical analysis here. So this is continuing on that same process where I should have read my slides through before I started recording this. All right, we're going through and taking, again, this is essentially what I was just discussing, is we're going through recognizing what a specific character sequence represents as a type and an associated attribute value. right? Recognizing that the character sequence FOO is supposed to represent an identifier, and we'll store a string as its associated attribute. So you're saying, okay, this is the type, and here's the specific value. Or I might look at the character's exclamation mark and an equal sign and say, oh, that's the not equal symbol. So you've got a token for not equals, a token type. Now, for something like that, you might not have any associated attributes, right? There's not extra information to associate with it. But this lexical analysis is going through this process of generating our tokens and their attributes. And then once we've got that, we want to go through and try and figure out structurally what does that mean. You know, is the sequence x equal 3 semicolon, does that represent an assignment statement, so to speak? Do we have a sequence of tokens that represents an if statement? Do we have a sequence of tokens that represents a while loop? You know, within that, do we have a sequence of statements that represents a print statement? So we're taking that token sequence and we're building up, we're reading that token sequence and using our knowledge of the grammar rules for the language to go through and see if the token sequence is actually valid. Does it actually express something that's correct in the language? And if so, what does it represent? What are the structures that it represents? So what we'll typically do is, at least abstractly, we'll go through and build a syntax tree that represents the structure of the program. So if you've got something like x is assigned y and a semicolon, then we're thinking, okay, that represents an assignment statement, and its pieces are a variable, the assignment operator, some kind of expression that's the value we want to assign, and then the semicolon to end it all. So again, your syntax tree, I've left the semicolon off here, our syntax tree might say, okay, at the top level, we've got this big abstract thing that's our assignment statement, and that's made up of an identifier, an assignment operator, and some kind of an expression. And that expression, in turn, is made up of an identifier representing a variable, for instance. So as we're going through performing our syntactic analysis, we're saying, okay, well, what does this structure represent? And again, this assignment statement might be just a small piece within a bigger part of the syntax tree that represents a while loop, and that might be inside a bigger part of the syntax tree that represents the program as a whole. So we're going through, our syntactic analysis is trying to read that stream of tokens and build it into this big abstract tree that represents what the program is supposed to do, or what the meaning, if you like, of the program is. Then the next phase was this semantic analysis that we talked about, where we've got the structure in the syntax tree that tells us what the pieces represent, but there's a lot more information that's not represented there. Again, rules like, if you're going to use a variable, it has to be defined before it's used, and it has to be in scope. And if you've got something like an assignment statement where x is assigned y, then they've got to be type compatible, right? Maybe if x is an integer and y is a string, that doesn't work. Right? So you have to be able to go through and augment that syntax tree with the extra rules and information that tell you how these pieces are supposed to behave relative to one another. What extra rules do they have to conform to? Now, quite often, as we're going through and doing that, we're going to need to keep track of other information. So as we're going through and working on our syntax tree, for instance, we might want to have a record someplace of all of the variables that have been declared, what their data types are, what scope they were declared in, that kind of thing. So this is where a symbol table comes in, where we've got a table someplace that keeps track of all of the things that we've defined so far, or all of the things that we've defined to this point in the program. So this is something else that we'll maintain as an additional data structure to keep track of what's going on and to support our ability to actually do the semantic checking and to make sure that x has been declared before we assign a value to it, and that y has been declared and they've got compatible types. So what we'll find is we build these syntax trees top down, and then we'll build up information from the bottom up as well. As the tree is evaluated, once we know what the value of y is, then we can determine if y is valid to match x. So for instance, if you're dealing with a language that's got dynamic typing, where the type of a variable can change over time. Sometimes it's got an int in it, sometimes it's got a string, sometimes it's got a float. You don't know in the beginning whether those things actually, whether the types are actually going to match. So there's runtime stuff to worry about, and if we're going through and producing a compiler for this, then maybe we want our compiler to introduce runtime checks at the point in the code where these kinds of steps have to take place, where we have to see, does y at runtime have a compatible type for x at runtime, and if so, how do we assign the value across? So there's all sorts of things that we want to build into our semantic analysis, if you like, and then we're going to need to deal with in our code generation at a later stage. All right, so the idea is, as we've built up this tree that represents the program, we've produced this kind of abstract representation of the program. It's no longer the original source code. It's this thing, this data structure that represents what the source code is supposed to mean. And so we've got this representation, and we might do all sorts of transformations on it. We might actually turn it into something completely different. Maybe we turn around and we've got this kind of abstract assembly language that we dump everything into and say, okay, here's my abstract representation of the program as this sort of virtual assembly language, if you like. So there's all sorts of different ways that we can come up with intermediate representations that are independent of either the source language or the target language that we're eventually going to produce code for. Again, at that point, we can go through and produce and do our machine-independent optimization. Optimizations that don't depend on the language that we're targeting. So yeah, I think I mentioned some of these earlier in the idea of if we've got code that's not reachable, or code that's not used, or code that's replicated, or code that's inefficient, are there things that we can recognize and rewrite at this point in the representation to produce a more effective version of the code, a more effective version of the program that is functionally equivalent, right? It's going to work the same, it's just going to work the same more efficiently. So these are things that we might want to consider, things to try and reduce the amount of branching. Maybe the original developer came up with a really inefficient way to lump together their collection of if statements and branches and exits and continues and that kind of thing. And maybe the compiler is capable of recognizing that and rewriting it into a more efficient form. So all sorts of possibilities here. Eventually, once we've got our optimized independent representation, we want to produce actual target code. And again, usually the first objective is simply to make sure that that target code is correct, that it does what the abstract representation says it should do. So we won't be as focused perhaps on getting perfectly optimized target code at first. We're just going to get something that works. So this is going to involve going through and trying to figure out, for our given abstract structure, if I've got this kind of abstract while loop, what sequence of instructions is best going to represent that in the target language? What data types do we need to use in the target language to get the effect? What addressing modes do we need to use? What new checks and bounds do we want to insert in there? Does the target language need us to insert boundary checks on array accesses or memory accesses? Or does it need us to insert type checking of some form, right, to get the same effect in the target language as we had in the source language? So we've got the mechanics of just trying to make sure that it does in our new format what we asked it to do in the source. And then once we've got that, then we can go through and start looking at optimizations. Are there things that we can do in terms of rewriting some of those sets of instructions to get better behavior? And this might target all sorts of different things. Again, we might be trying to minimize the size of the executable. We might be trying to produce the fastest runtime. We might be trying to reduce the number of page faults that we get. All sorts of possibilities in terms of optimization. So we have to decide which ones we do and don't want to take into it. We do and don't want to perform. And it's entirely possible, since this is an incredibly complex process, it can be very challenging to ensure that the optimizations that we're performing and the sequences of instructions that we're selecting really do produce the same effect in the target code as we wanted in the source code, right? It can be an incredibly complex problem to make sure that we get exactly the behavior that we want out of the compiled result. All right, just in terms of terminology, we quite often talk about front end and back end and maybe a middle section for a compiler. Usually for the front end, we're talking about that part where we're going from the character sequence in the original language to that intermediate representation. And then we're talking about the back end as being going from our optimized intermediate representation to the actual target language, where we're generating code in the target language. And then whatever's happening in the middle, whatever sequence of rewrites and transformations and optimizations is kind of that vague middle ground. And so you'll see people or see discussions about compiler development that just talk about the front end and the back end, and they kind of assume that the rest of it happens in sort of one side or the other, or cases where there's a distinct middle ground where the optimizations take place. Again, all of these choices are kind of a point of view on where you decide to draw the line between things, but they are pretty common terms, and they are things that we'll make reference to over the course of the term. All right, so the idea is we now have a reasonable idea of what's going on during the compilation process. Where we'll go starting next week is to get into the mechanics of how to make that happen. And so we're going to start by looking at tools to produce a lexical analyzer for us and to produce a parser for us. So we're going to look at Lex and Yak, two tools that take a grammar describing a language, and for us they produce the tool that will actually eventually they'll produce a compiler for us. But they produce the tools to do the tokenizing and to do the parsing for us. So that's where we'll go next week. I will leave it there.